Yeah, we were examining the elementary properties of Markov processes, and let me continue with that, give a little more bit of an introduction to some elementary Markov processes, and then we go on to applying whatever we have learned to dynamical systems, specifically to coarse grained dynamics. If you recall, I defined the Markov process as one in which the conditional probability for an event to occur at a certain instant of time is dependent only upon the preceding instant of time, whatever happened at the preceding instant of time. And this short term memory led to the consequence, had the consequence that the entire family of probability densities or probabilities for a Markov process are in fact expressible in terms of a single conditional probability. And this means that the system is completely known, all statistical averages can be found once I give you an equation for this conditional probability or probability density. In the case of processes in continuous time, this probability density obeys a certain master equation, and the way we wrote this equation was delta over delta t p of x and t given an initial value x naught was written on the right hand side as equal to an integral over all intermediate states x prime p of x prime t x naught multiplied by the transition probability to go from x prime to x, the transition rate to go from x prime to x, minus p of x t x naught multiplied by the transition rate to go from x out to x prime. And this was like a gain term and that was like a loss term, and this is what the master equation read, and this thing is called the master equation. And I further pointed out that if you took these quantities and wrote these out as some kind of column vector, then you ended up with a matrix equation in the case in which the value of x, the values of x were discrete values, a discrete set of values. Otherwise it is an integration or replaced by a summation in the case of a discrete set of values. This kind of equation is not easy to solve. It is a linear equation in P, but it is an integral differential equation on this side, and it is not altogether trivial to solve it, although there are well established techniques now for handling this sort of equation and making considerable progress. Of course the input information has to be this, you have to know what these transition rates are to go from one state to another. The same thing if I wrote it out in discrete time for a discrete set of states, and let us say the variable x takes on only a discrete set of values x1, x2, x3 etc., and let us label that by some integer j, and let me say the system is in state j if the variable, random variable, has a value x sub j. Then I can ask what is the probability that it is in the state j at time n or time n plus 1. What is this equal to? This is equal to the probability that at time n the system has reached some state k, for example. In this case let us put the time index inside because we are going to write this as a matrix equation. So p j at time n plus 1 is p k at time n multiplied by the transition rate of making jumps from the state k to the state j per unit time. So in one more step it jumps to this point, and in our notation this thing is a summation over k, and in our notation this is a transition from k to j. The way I have written it from x prime to x, I write this as from k to j. This is the gain term, so this stands for the transition probability from k to j, minus pj of n w kj. So again this is now in the form of a rate equation. It really is telling you that here is the gain term which contributes to the probability in state j, and this is the loss, the rate of loss. And if you write these pj's together as a column matrix, then of course this is a matrix equation of the form p is p at time n plus 1 is equal to some w p at time n, and since this is a constant matrix which you are given once and for all the transition rates between the different states, it is immediately obvious that p at time n is w to the n p at time 0. So this at once implies that p at time n is w to the n p at time 0, and all you have to do is to calculate this matrix here. Now the way to calculate the nth power of a matrix for large n, if this state space has got some large number of dimensions, is not altogether trivial. What you do is to try to diagonalize this matrix, or at the very least if you can't diagonalize this matrix, at least bring it to Jordan canonical form, after which you can take its nth power without too much difficulty. So this is a problem now in matrix algebra to find out what Pn is given any initial distribution P0. Let us look at a few examples. Let us look at an extremely simple example in continuous time, just to get used to the idea of these things in continuous time, and let us look at an example where the state space just contains, it's two dimensional, just two possible values. So we have a variable which switches between two values, say x1 and x2 at random instants of time, and what would this look like if I plotted the graph? So let us say there are two values x1 and x2, so as a function of t I have the variable x, and suppose this is the value x1 and this is the value x2, just for illustration's sake let me take it to be negative, it does not matter. So this is the value x2, it continues for a while and then flips back to x1, goes on for a random instant of time, back to x2 for a random instant of time, and so on. So here is state 1 and here is state 2, and there is a certain transition probability or rate per unit time of switching from state 1 to state 2, and let us call that lambda 1. So lambda 1, so 1 to 2 rate of switching, this is lambda 1, and 2 to 1 back again, this is lambda 2 in general. And suppose this process goes on for a very long time, and now I ask what are these equations, what is dp1 over dt equal to, and what is dp2 over dt equal to. It is evident that at any instant of time p1 of t plus p2 of t must be equal to 1, the system must be in one of the two states, and it flips back and forth between these two states. Now what would this equation be equal to? If the system has reached the state 1 already, it makes a transition to 2 with a rate lambda 1, and that is a loss term for P1, so that is minus lambda 1 P1, because they are switching out of 1 into 2 like this, and then the gain would be if you switch from 2 back to 1, and that would be plus lambda 2 P2. On the other hand, here for P2 what would it be here? Obviously lambda 1 P1 minus lambda 2 P2, okay. And this is as it should be, because as you see the transition matrix, if I write it down, is in fact, so W in this case, this transition matrix is minus lambda 1 lambda 2 lambda 1 minus lambda 2. And as I promised, the sum of elements of each column is 0 as you expect, and it has the immediate consequence that if I added up P1 plus P2, I immediately get, as you can see, d over dt P1 plus P2 equal to 0, which implies that P1 plus P2 equal to constant equal to 1. If you normalize it initially, it remains at 1 for all time. The job of course is to now try to find out what are the steady state properties of this system by this process, by the way, where it flips, by Markovian process where it flips between two possible values back and forth, is called a dichotomous or dichotomic Markov process, very often abbreviated as DMP. Very popular in modeling in a very large number of situations, and it is evident immediately that I can eliminate either P1 or P2 and I am going to get a second order differential equation for either P1 or P2, the same equation in fact, and then the solution depends on the initial conditions. So the solution would in fact be the sum of two exponentials depending on the eigenvalues of this matrix, which are fairly straightforward to write down. Okay. We can in fact compute e to the Wt and write down the full answer. You can do this in some simple form, but first let me ask this: what is the average value of x in this case? This is an ongoing process for a very long time, so you could ask what would be the equilibrium value, what would be the equilibrium value, so that is, or a stationary value. Equilibrium probability distribution, what would that be? Well, exactly as in the case of dynamical systems, we essentially have a system which looks like this, and in equilibrium this should be 0 in the stationary state. So you want Wp to be 0, and if I call that let us call this P1 equilibrium and P2 equilibrium, this column vector tells me what the equilibrium distribution is between 1 and 2. What would that be for this process? I would have to set this equal to 0. In other words, I would have to find a column vector P which is annihilated by W. You act with W on the left and you get a null vector. Because the rows, the sum of each column is equal to 0, it is evident that the uniform vector is a left eigenvector with eigenvalue 0. So it is evident that if I took this 1 1 and operated with W on this side, I get 0. That is because the sum of each column is equal to 0. So what I want is the corresponding ket vector, right eigenvector corresponding to this 0, and that would give me the equilibrium values out there. But you can actually guess on physical grounds, you can guess what happens here. What is the average time that the system spends in state 2? What would this be? Let us call this tau 2, mean residence time in state 2. Let us call that tau 2. What would this be? What would the mean residence time here be? And similarly tau, the mean time here would be tau 1. What would this be? Well, it is clear the faster it gets out of that state, the less the residence time in that state. And if it goes on for a very long time, then what you could do is to add up all these intervals and divide by the total time and take the limit in which the total time elapsed goes to infinity, and similarly for state 1, and this would give you the relative fractions, the fraction of time that the system spends in either state 1 or state 2 over a long interval of time. That would be in fact directly proportional to your equilibrium distribution. So what would that be? What is tau 2 going to be? Exactly, it is just what, exactly, absolutely. So this thing here is lambda 2 inverse, and this is lambda 1 inverse. Lambda 1 is the rate at which it switches out of 1, right. So lambda 1 inverse is the mean time it spends in state 1, and therefore this P1 equilibrium would be equal to tau 1 over tau 1 plus tau 2, and the other guy is tau 2 over tau 1 plus tau 2. Therefore, this is lambda 2 over lambda 1 plus lambda 2, and this other guy is lambda 1 over lambda 1 plus lambda 2. Now that is physically obvious. It is easy to trivial to check that if you took this and wrote down here those column vectors, this column vector here with tau 1 is lambda 1 inverse and tau 2 lambda 2 inverse, you get 0 on the other side. What would the average value of this process be? What is x average equal to?
x1 into this probability.
Well, exactly. So I would expect this to be x1 tau 1 plus x2 tau 2 over tau 1 plus tau 2. This is what I would expect. And that would be equal to lambda 2 x1 plus lambda 1 x2 over expect this to be the average. So it is sitting somewhere here. It depends on whether it is closer to this or this, would depend on what the transition rates are in general. And similarly for the mean square, and that would just be x1 squared and x2 squared here, that is it. And you can find the correlation function, that is the crucial thing we would like to find out. Now what do you think that is going to be? That is the most important thing of all. So in particular I would like to find the correlation function and let me call this C of t in equilibrium. This would be equal to the average value of x minus x average, x of 0 minus x average, x of t minus x average, and the average value of that. That is my definition of the correlation function. And what do you think this is going to be in this process? You can compute this without too much difficulty, but let us see what the exact expression for this quantity is, what the actual expression for this is, the formal expression. If I say that so this is equal to, if it is a continuous process for example, I would say this is equal to an integral over the initial value dx naught, an integral over the value at time t, let me just call it x, times the probability that I have x at time t given x naught at time 0 multiplied by the probability that I have x naught at time 0, since it is a stationary process there is no time argument there, multiplied by x minus x average times x naught minus x average. That is the quantity which I want to average over, and this is what I average over, this probability distribution. This is the conditional probability density and that is the probability density, stationary density of the process. Now of course I have discrete values 1 and 2, so each of these is summed over x1 and x2, and instead of these densities I write down the probabilities themselves. So it is a straightforward calculation, you can complete this fairly straightforwardly. Let us look at what these probabilities themselves are in the simplest instance. So to make life a little simple, let me do the following. Let us take x2 to be minus x1 so that it is completely symmetrical, and let us call this value some constant value c, and the other value is minus c, etc. Minus c, so it flips back and forth between plus c and minus c, and for algebraic simplicity let us suppose the transition rate is just a constant lambda. So this is some tau equal to lambda inverse, and this average value is again tau equal to lambda inverse average on either side. The average duration in each state is some tau which is the reciprocal of a single common rate of lambda of switching from 1 to 2 and 2 back to 1. So this just becomes this quantity here, nothing more. Then it is easy to compute. So I write P of t once again as equal to e to the wt P of 0, whatever be my initial distribution, and what is e to the wt, it is this, but this is equal to, I need to exponentiate this, I find its square and its cube and so on and so forth. So let me write this as minus lambda times the unit matrix plus lambda times a matrix which is essentially 0 1 1 0. So this becomes e to the minus lambda t, because I have e to the power a matrix plus another matrix, and e to the a plus b is not e to the a times e to the b unless a and b commute with each other, but in this case a happens to be the unit matrix which commutes with everything else. So that is the reason I chose this special case. So it is e to the minus lambda t, and then it is the exponential e to the lambda t times this matrix 0 1 1 0. The whole thing acts on P of 0. What is the square of this matrix? Well, let me call this matrix, it has got a name, minus lambda I plus lambda, let me call this matrix sigma 1. And then notice that when I exponentiate this sigma 1, things are very, very simple, because what sigma 1 squared? It is the unit matrix, right. So this becomes I once again, right, and what happens next? 3 factorial sigma 1 cube, but sigma 1 squared is the unit matrix, so it is just sigma 1 plus dot dot dot, and I gather all the i's together, and I have 1 plus lambda squared t squared by 2 factorial plus lambda t to the power 4 over 4 factorial, etc., ad infinitum, and what is that equal to? Plus I have another matrix which is lambda t plus lambda cube t cubed over 3 factorial plus lambda 5 t 5 over 5 factorial plus times sigma 1. So what is this equal to? Yeah, it is equal to cos hyperbolic lambda t times I plus, and this is sine hyperbolic lambda t times sigma 1, that is it. Therefore this thing here is now exponentiated, it is finished, it is equal to e to the minus lambda t times this matrix. So that matrix is just this, cos hyperbolic lambda t sine hyperbolic lambda t, on this side sine hyperbolic lambda t cos hyperbolic lambda t, it is that matrix acting on P1 of 0. So let us write that explicitly, P of 0, that is right. And you begin to see immediately that it gives you exactly what you would intuitively expect directly, and that is the exact solution to this coupled differential equations, which we circumvented by simply writing the matrix solution down right away, and therefore P1 of t, P2 of t, if I write it as a column vector, this is equal to e to the minus, so let us write this out explicitly, solution, P1 of t is equal to, and P2 of t is equal to, there is an e to the minus lambda t cos hyperbolic lambda t times P of 0. So this gives you e to the power minus lambda t P1 of 0 plus sine hyperbolic lambda t P2 of 0, and similarly that is it. So it gives you explicit solutions. If I start with the system in say the upper level, then P1 of 0 is 1 and P2 of 0 is 0. What happens? As you can see, the probabilities flip back and forth. So if P of 0 is equal to 1 0, then this quantity here becomes equal to, this is 0 here, so it is just this, and that is equal to 1/2 1 plus e to the minus 2 lambda t, and that is it. And in that same case, this becomes equal to half, there is an e to the minus lambda t, so this becomes 1 minus e to the minus 2. So at t equal to 0, this is 0 and that is 1, and as t increases, this fellow drops down from a number from 1 towards half asymptotically, and this builds up from 0 towards a half. Pardon me? Yeah, there is a bracket over here, right, right, okay. And what does the correlation function become? What do you think the correlation function would be? And what are the steady state probabilities? What is the equilibrium distribution in this case? Just half and half. It is clear that the number, the average durations are equal and it is half and half, but that is precisely what you expect this to become as t tends to infinity. That is a check that there is sufficient mixing in this system, that the conditional probability tends to the stationary probability as t tends to infinity. The memory of the initial condition is gone, and that is exactly what has happened here. It is not hard to show that the correlation in this case, C of t, the average value is 0, so we do not even have to subtract the average, and this quantity is equal to what? If the value of the random process is plus c or minus c, when I take averages and I multiply the two together and I square it, and if I want the correlation function, it becomes clearly there is a c squared which appears here, c of 0 must be equal to 1, and then it is multiplied by, if I compute those averages, it just turns out to be e to the minus twice lambda t. It is exponentially correlated with the correlation time which is 1 over 2 lambda which is 2 lambda inverse. That is the time roughly on which this, that is the time scale on which the correlation, this the memory acts. That is not surprising because there is just one time scale in the problem, so you end up with something which is proportional to lambda inverse here. There are many processes which are exponentially correlated, Markov processes. There could be in general more time scales, there could be a sum of exponentials, but when processes are exponentially correlated with a single correlation time, something very special happens, and the DMP is a classic instance of such a two-level system, a two-state process. You can add asymmetry to it, you can change the rates and so on and so forth, but the essential physics does not change. Very common in modeling, very popular in modeling. It is clear that it models something which is either on or off, a two-state system is either on or off. You can make a three-state system where it is on or off, and then there are quiescent states, there are active states and so on. Those are generalizations of these two-state processes. Okay. We could make things a little more complicated. You could say, well, and this is a very popular process, so let me mention that. There is a class of jump processes where you end up with the following situation. The variable x takes on a continuous set of values and there is some equilibrium state, there is some equilibrium distribution p equilibrium of x, some equilibrium probability density. Then in the Markov process, for which the transition rate is of this kind, this is the transition probability rate or per unit time to go from x prime to x, we could model this in the following way. We could say, well, this thing is a rate, so there is a time scale lambda inverse sitting there multiplied by something which depends only on the equilibrium or final state distribution. So you could say it does not depend on where you are, but it instantly jumps and with something which is proportional to p equilibrium of x. This too occurs in many physical situations. So the jump rate is independent of the initial state, depends only on the final state, and that too in a manner which is directly proportional to the stationary distribution itself. I urge you to solve the master equation with this assumption. This is a normalized density, so if you integrate this over all x, you assume it to be equal to 1, and then it turns out you can actually solve for the conditional probability density p of x comma t given x naught. You can actually solve this exactly and show that the process is exponentially correlated. So it generalizes the idea of this two state process to a continuum of states in a specific direction. So once again I leave you to work this out and show that the correlation is exponential, there is an exponentially decaying correlation. We will again talk about Markov processes, we will again talk about similar considerations, but let us go now change horses and go completely back to dynamical systems and see how a specific coarse grained dynamics is in fact a Markov process. This is what I would like to do, and I would like to show you that the dynamics is exactly that of a Markov chain, which is the sort of thing we examined here. And now just to make things a little less accidentally degenerate, let us look at the tent map once again of the unit interval, but we will make it an asymmetric tent map just so that we do not have artificial degeneracies, and there is a specific reason why I do so. So let us take, instead of a tent map which goes up and comes down to half, let us say it goes up in this fashion and comes down there for the rest of it, and let us suppose this is some number a which is less than a half. So 0 and 1 here, and this is unity here, and this is my map function. So this is how xn plus 1 is given xn. I call this the asymmetric tent map, and the map function is the following: xn plus 1 is equal to, it is clear, it is xn divided by a for 0 less than equal to a. The slope is 1 over a because it reaches 1 when xn is a, and what is the slope here? It starts at 1 and goes to 0, and therefore it must be 1 minus x, and the slope is 1 minus a, because if a is a half, it is also a half, it is also 2. So a less than equal to xn less than equal to unity. Okay. Now this map is fully chaotic, and what I am going to do is to partition it into two cells, a left and a right, and the natural thing to do is to partition it from 0 to a as one cell and a to 1 as another. So let me call this left, and let us call this the right cell, and similarly for xn plus 1. Okay. What is the invariant density of this system, of this map? So we write the Frobenius-Perron equation once again. I have rho of x equal to integral 0 to 1 dy rho of y, a delta function of x minus f of y, in this fashion. And that is equal to, well, since I am breaking this map up, there is a 0 to a which is one piece and an a to this which is another piece. So this is equal to 0 to a dy rho of y, a delta function of x minus y over a, because that is what the map function is in this region, and then a piece which is a to 1 dy rho of y, a delta function of x minus 1 minus y over 1 minus a. That is the Frobenius-Banach equation, and in the standard procedure we convert this to a functional equation and see if we can guess a solution to this equation. So I pull out this a, y becomes ax, so it is rho of ax, but if I pull out this a from the denominator it goes up here in the numerator there, and similarly plus 1 minus a, this factor comes up, and then a rho of, now y here is equal to, so 1 minus y becomes equal to 1 minus a times x, so y becomes equal to 1 minus a x. So this argument is 1 minus a times x. That is the Frobenius-Banach equation in this case. What is the guess solution? Yeah, the fact that this and that seem to cancel each other suggests that you put rho equal to a constant again. So yes, indeed this is true, rho of x equal to 1 is the unique normalizable non-negative solution to this equation. So it is a uniform density once again, it does not matter whether it is a symmetric tent map or asymmetric, it is uniformly spread out. Now I am going to do the following, I am going to ask what is the transition matrix to go from one cell to another. We write this W down completely for this chain, and then we test if this is a Markov process or not by finding out whether the two-step probabilities is just the square of the same matrix which you get in the one step. If it is, we know that it is a Markov process, or the n step probability is just some transition matrix raised to the n. If so, if that is computable on both sides and you verify that this is so, then it is as good as a Markov process, but we need several steps to do this, and let us do that carefully. First let us ask what is the, so my cells are here, and this by the way is A also, so this is cell left here and that is right here, and this is left here and right here for the one step transition. Okay. First I ask what is the measure of the left cell, what is this equal to? That is clearly an integral over the left cell which is 0 to a dx rho of x, that is obvious, that is the definition of the invariant measure, just the integral of the invariant density over the cell. Okay. And since this is constant equal to 1, this is a, and mu right equal to 1 minus a, so that is certainly true, right. I need to calculate the transition probabilities. So I need to calculate quantities like the probability that if I start at 0 at time 0 in the left cell, I am at, so L at time 0, I remain in the cell L at time 0. I need to compute this number, that is a probability, pardon me, at time 1, at time 1, at the end of one time step. So let us put the time steps here. Similarly, I need to calculate PL1 given that I start at R on the right hand side, or PR1 given that I start at L0 and PR1 1 given that I start at R0. I need to calculate these probabilities and then I am going to put that in the form of a matrix, call that my transition matrix at each step. Now how do you define these quantities? What would you do? Remember that the x itself is continuous, but I have broken up the whole thing into cells and I am now looking at the symbolic dynamics of the cells. So the states of my system are either L and R and that is what I have written here. These are the probabilities I am computing. But how do I write this down? For example, how would I write this down? What would be the procedure to write this down? From first principles I would like to know what is P at L1 at L0. I have to be a little careful now. So I say, well, what is the joint probability that I am at in the left cell at time 1 given that I am in the left cell at time 0. So I start with this quantity here and ask what is this joint probability, and this, as you will see intuitively, is equal to an integral over dx naught. Suppose x has the value x naught at 0 time, so it is an integral over dx naught over the L cell, an integral over dx1 over the left cell multiplied by what? Since x is continuous, we are talking about probability densities, right. So this is multiplied by the probability, invariant probability that you are in the cell L. You have the invariant probability for this variable x naught, rho of x naught integrated over L, that gives you the probability of starting in L, multiplied by the probability density for starting at x naught and moving to an x1, and that we know is a delta function kernel, and we know that that is equal to this. This is a conditional probability density. It says if you give me an x naught, I am guaranteed to go to an x1 whose density is given by this, and that multiplied by rho of x naught gives me the joint probability density for x naught and x1, x naught at time 0 and x1 at time 1, and it is integrated over x naught and x1 over the regions that you are interested in. So this is in fact the definition of this joint probability, right. But what is that equal to? What is this equal to? Well, x naught L, the cells L is just 0 to a dx naught, and it is just 0 to a once again over dx1 on this side, and rho of x naught for this map is 1. So you do not need to put that in, but you do need to put in delta of x1 minus f of x naught, this function, and this function was what? X over a, so it is x naught over a, because that is what the branch on the left is. So delta of x1 of x naught over a. Okay. I need to compute this integral. So the range of integration, the region of integration, you can do this geometrically in the following way. One way would be to convert this to an integral delta function over x naught, finish that and then do the x1 integration, but I can do it as it is because I also have to integrate over x1. I may as well do it directly provided the delta function fires. And when will that happen? Here is the region of integration, this square, and here is the delta function constraint which tells you that x1 is f of a, f of x naught. So what is the value of this integral? No, what is the value of this integral? Of course it does. For all x naught between 0 to this point, wherever this intercept is, for every x1 in this region of integration between 0 to a, that delta function fires. So I can do the x1 integration provided I restrict the x0 integration to this region, otherwise the delta function does not contribute. And what is this point, this value here? It is a squared, it is a squared, because a squared over a will give you this value a. So this integral becomes equal to 0 to a squared dx0, and now the delta function has taken care of, has become 1, because this integral is finished here, and the answer is a squared. Right. Therefore, what is this equal to? That is the conditional probability for this L to L. Exactly, so it must be this quantity is this quantity multiplied by P of L0 is by definition equal to P of L1 L0. The joint probability is the conditional probability multiplied by the absolute probability here. Therefore, this quantity alone is this divided by P of L0. But that is equal to a squared divided by, what is this equal to? P of L0. Yeah, it is the invariant measure, because it says what is the actual stationary probability of being in L. I close my eyes and put my finger on this this interval, and what is the probability I am here or there, and it is just mu L, which is equal to A. So we have an A here. What is this going to be? Well, let us do that. Let us see what that thing is. So again it is over L dx0, but this becomes an R, and now I am trying to compute P of R1. So this is finished. This is over R, and I have to do this integral, and what does that become? I use the same strategy as before. In this case, since the invariant measure is unity, it is actually very simple. I have to integrate over this quantity here dx0 over L, but dx1 I integrate over R. So really it is this range of integration that I am talking about, and this range of integration, for every value of x1 I have a contribution from the delta function provided x0 runs from here to there, and therefore this is equal to integral, and that runs from a squared to a, from here to there dx0, and then the delta function contribution over x1 gives you unity for the x1 integration. So it is a times 1 minus a. So this guy gives you a times 1 minus a, but then I must divide, in order to get this conditional probability I must divide by the measure of this cell here, mu of L, which is an a, and therefore this just gives me 1 minus a. Similarly for the other one, P of L1 R0, I have to integrate over this rectangle, and the contribution that's non-trivial, the only contribution comes from this region. Now what is this point? Remember, this function is 1 minus x0, so this is x0 here and this is x1, it is 1 minus x0 over 1 minus a, and that is equal to a, because that is the value here. So it tells you 1 minus x0 equal to a minus a squared or x naught is equal to 1 minus a plus a squared. So this point is 1 minus a plus a squared. Therefore, if I integrate we are now doing L1 and R0. So this is over R, this is over L, and that integral is this interval, and it is 1 minus this guy, so it is a minus a squared is a times 1 minus a. So this quantity here is a times 1 minus a, but then I need to divide by the measure of this cell to get the conditional probability, and that is a 1 minus a, and therefore it is just a. And finally we need to know this length and divide by the measure of the right cell, because we are now integrating over this region, and that length is 1 minus a plus a squared minus a, it is 1 minus a the whole squared divided by 1 minus a to get the conditional probability, just gives me a 1 minus a. So this here is an a and a 1 minus a on this side. The sum over each column is 1, therefore it is a stochastic matrix, a matrix with non-negative elements such that each column adds up to 1 or each row adds up to 1 is called a stochastic matrix, because it is connected to these probabilities. And such a matrix would have a uniform left eigenvector. Had the row sums been equal to 1, it would have a uniform column vector as the eigenvector. So it clearly has 1 as an eigenvalue and a uniform left eigenvector, and the corresponding right eigenvector is not hard to find. It would be related to some equilibrium distribution. In this case it would be related to a and 1 minus a itself. So this gives me my transitions here, the transition at one time step, and the question is can the transition matrix at 2 time steps be written as the square of the transition matrix over one time step. So if I call this some transition matrix T, it is related to the W that I wrote down earlier by the addition of a unit matrix here. Then the question is what is T squared, and is that the same as, so the question we ask is the following, is, and I leave you to verify this, is the matrix P of L at time 2 given L at 0. Is this matrix equal to T squared is the question. If it is, then you have reason to believe that this is a Markov chain, because all you are doing is to take this transition matrix, one step transition matrix, and multiplying it, raising it to higher and higher powers. Now what would you do to compute this? Yeah, what I do is to first compute this L2 L0, and I write this as over L dx naught, let us just call it alright x naught over L dx2 times rho of x naught, which is unity in this case, multiplied by a delta function of x2 minus f2 of x naught. So I take the second iterate of this map and play the same game and compute these numbers, which are very easy to do in this case, and check out whether that is equal to the square of this guy or not. of this matrix here? If so, then by iteration, by induction, I know that this is true in the nth step as well. I leave you to verify that this is indeed so. This is a Markov chain, which is equivalent to saying that this partitioning that we have done of the phase space in this map is a Markov partition, because the symbolic dynamics of the system has been reduced to a Markov chain in discrete time, and therefore I can use the entire machinery of Markov chains to solve various problems here. For instance, I could ask questions like, if I start with the cell L, then what is the mean time for me to come back to the cell L, because it undergoes excursions from L to R, it stays in L for a while, etc. So if it leaves L after a time step, what is the mean time for it to come back, what is the statistics of these recurrence times, and so on. So the entire machinery of Markov chains, for which well defined answers exist for such questions, can be used in order to study the dynamics of this system. You do not have to go back to the map anymore, because that dynamics has been now transferred to the properties of this Markov chain. It carries all the information that you need. This transition matrix already carries everything. So we will study this a little better, because I would like to do two things. I would like to show you that there is a uniform, there is a very specific behavior of the recurrence statistics, namely when the system comes back, because it is ergodic, you know that the system will come back to whichever cell you leave given enough time. Then a question of interest is, how long does it take to come back, what is the statistics of the recurrences, are the successive recurrences independent of each other or not, and so on. Well defined answers to these exist, and we will use this as a sort of case history to study this a little deeper, and I will do that next time. Let me stop here today.